Hey, welcome back, and we're going to talk about aqueous solutions. Water, of course, being the universal solvent. A solvent is something that does dissolving, and it does a remarkable job of dissolving many different types of substances. In our next section here, aqueous solutions, a solution will be discussed in which water is the solvent, and what is known as the solute is whatever goes into the water and dissolves. To be soluble in water, it simply means that it's able to be dissolved. Things like salt, sugar, ethanol, sulfur dioxide are all examples of things that dissolve quite readily in water. Is my pen not moving? There we go. So let's take a look. Table salt has a formula known as NaCl. Sodium chloride. Sodium is an ion that carries a +1 charge. Chloride is an ion that carries a -1 charge. And we've talked a little bit about this, but it's really coming up heavy in our next lesson here. Sodium with its 1 valence electron lives in group 1A. Chlorine with its 7 valence electrons lives in group 7A. It would have 7 dots around it. They do not share a pair of electrons. That would be called a covalent bond, but instead what we'll see is that they actually transfer an electron from the metal to the non-metal, and we set up what's called an ionic bond, an electron transfer. When a sodium loses an electron, it forms an ion of a +1 charge, loss of an electron. Loss of 1 electron. And here, if chlorine gains that electron, now it had 7, but now it gained an extra one. Gaining an electron made it become a -1 charge. I'm sorry, my pen is acting up. So gaining 1 electron made it a negative charge. So we're going to refer to this as an ionic compound. An ionic compound is built of ions, and ions are charged atoms. Those charged atoms can be positively charged or negatively charged, and when they actually form a compound, they transfer an electron, sodium donating it over to the chloride, resulting in an ion. Many salts, which are all of these types of categories of ionic compounds are just commonly referred to as salts, are very much water soluble, and you can see why. There's a positively charged area that's going to be attracted to the water's negative area on the oxygen. There's a negative ion that would be very much attracted to the hydrogen portion of the water, the positive region. We know opposites attract. Salt is an ionic compound. Ionic compounds tend to dissolve well. Sugar, with its formula, and we're going to look a little bit later on, sugar, one type of sugar molecule is called glucose, has lots of OH bonding in it, and it's said to be a polar molecule. Anything that is polar has regions that are positive and negative within the same structure, just like a water molecule, and because they have O's and H's in the same structure, they're going to be attracted to one another. Same with ethanol. Ethanol is a polar molecule. Sulfur dioxide is a polar molecule. Things that are not able to dissolve in water are things that are non-polar. All these long hydrocarbon chains, such as oil or gasoline. Do you remember learning that the major component of gasoline was a molecule called octane, and it was literally 8 hydrocarbon elements, 1, 2, 3, 4, 5, 6, 7, 8 of those right in a row, totally non-polar molecule. Nothing unusual about that molecule, just all C's and H's bonded together, creating a non-polar situation. And so therefore, non-polar and the water polar do not blend. We're going to learn a simple little rule called likes dissolve likes. Polar will dissolve in polar, non-polar with non-polar, but never the two shall mix together. So here's some words from our previous slide clearly defined. A solution is a homogeneous mixture of a uniform blend. Back when we first met each other in Chapter 1, we defined classification of matter. Matter that is a blend of many things but looks uniform throughout was called a homogeneous or homogeneous mixture. A solution has two components, the solvent and the solute. The solute dissolves in the solvent. So whatever I have the greater amount of, typically water, is the solvent, and what you have less of is the solute. We're going to talk about aqueous solutions in our water chapter. So if we had salt water, salt would be the solute, water would be the solvent. The concentration terms we might encounter in a laboratory setting or hospital setting. First of all, parts per 100. If I had 20 grams of table salt called sodium chloride dissolved in 100 grams of water, I would have a 20% saltwater solution. So look what we've done. The 20 grams of solute in the 100 grams of water create 20%. So 20 parts in 100 parts expressed as a percent is simply 20%. Parts per million is parts over 1 million grams of water. If I had 1 gram of the solute, say it's salt again, in 1 million grams of water, it would have 1 part per million. Parts per billion is 10 to the 9th, isn't it? So if I had 2 parts per billion of mercury, that would represent 2 grams of mercury in every billion grams of water. Notice what's on the bottom is just the water component for our concentration terms of percent. So just to kind of think about that, grams of solute over grams of the solvent, which we know in this particular chapter will be all about water. If we want water to be in parts per million or parts per billion or as a percent, percent is out of 100 parts, parts per million is out of 1 million parts, and parts per billion is out of 10 to the 9th. But always grams of solute per 100 grams, per million grams, per billion grams gets our ratio. But a more common unit is called molarity. Big M, capital M, is our unit for molarity. Molarity is defined as moles of solute per liter of solution, and you'll often see this bracket representing the concentration of. Now we need to remember from our previous unit also the unit called mole can be calculated by finding the grams of solute over the molar mass of your solute. Remember that term molar mass, the weight of each atom over, off of the periodic table, just summed together. The molar mass found on the periodic table, the weights of each individual atom summed together, and the ratio of grams over molar mass is a mole. Taking that mole per liter of solution gets us this concentration unit known as molarity, capital M. So if I think about seeing this bracket of sodium chloride, what this is telling me is, when I see a bracket like this, it's representing a saltwater solution. It would tell me that if I had 1 molar sodium chloride, I would have exactly 1 mole of salt dissolved in a liter of solution. Let's break that down a little bit further. The molar mass of sodium on the periodic table, I'll round to be 23 grams per mole. The molar mass of chlorine, you find it on your chart, I'm going to call that 35.45, so I'll call it 35.5. The sum of the two atoms when added together is the definition of molar mass. Sodium chloride has a molar mass of 58.5 grams. Now I'm doing that to remind us, how do I go about actually making a 1 molar solution of salt? And this is a nice picture here to kind of help me illustrate the process of making a solution. How do I make a 1 molar salt solution? Remember the word molar, moles per liter. And remember what mole was grams over molar mass. We just determined on the previous slide the molar mass of sodium chloride to be 58.5 grams. And if I weighed out 58.5 grams on the scale, we'd have exactly 1 mole. So the very definition of the term mole, how much do I weigh out to get 1 whole mole? We defined that term to be the molar mass. The sum of an Na added to Cl, I'd weigh out on a scale 58.5 grams. Alrighty, so let's kind of visualize. This is something called a volumetric flask, and what you see is a little etch mark on this piece of glassware right up here. I'm going to walk to the scale and just pour table salt on the scale until it measures out, and it'll be a big heaping pile of it, but 58.5 grams of table salt. With this little volumetric flask, I'm going to fill a little bit with water first. A little bit of water first, then I'm going to dump in my salt, my 58.5 grams of salt, and I'm going to start to swirl to start the process of dissolving. Some of it may stick, you might have to shake around a little bit. Then I'm going to continue adding water up until exactly I reach this 1 mil mark, or I'm sorry, this 1 liter on this etching. Sometimes I put a lid on this and invert it up and down, stopper it and mix well, and we will have added 58.5 grams to a water that gives me a complete volume of 1 liter. Now remember, the salt takes up some room, so the reason I don't add 1 liter first and then pour in the salt, I'll have overshot my point. So I add a little bit of water, then pour in the salt, and then the remaining volume with water until I get a total of 1 liter. I don't want to exceed the 1 liter, I'll have a diluted solution. How much do I weigh out to get 1 whole mole? That's the definition of molar mass. When I want a 1 molar solution, I weigh out 1 mole and dissolve it into 1 liter of water and mix well. What would the concentration in molarity, see the big M, and mass percentage of the resulting solution be when you add 5 grams of sodium hydroxide NaOH to 95 mils of water? Well, let's do molarity first, just because it was written first. Molarity is defined as moles of solute per liter of water. And I know that moles is defined as grams over molar mass of our solute, and we'll still want that all over the liter. So we're going to do a little mole map work here. I look on the periodic table and I find the molar mass of the element sodium. My pen stopped moving. There it goes. So Na, I'm going to call that exactly 23 on the periodic table. And oxygen has a molar mass of 16, and hydrogen with its molar mass of 1. Add up an Na, an O, and an H, and we get 40 as the molar mass. 40 grams per mole, the molar mass of NaOH. So we walked over and we weighed out 5 grams of NaOH. We're going to place that over the molar mass we just found to be 40 grams per mole. By placing the ratio of 5 over 40, we're solving for the term mole. Mole is grams of solute divided by its molar mass, 5 over 40. And what about this bottom number, the liters of solution? Well, right now we have 95 milliliters. I cannot place 95 down here because it's the wrong unit, but it's a simple decimal slide. I want a liter, and I know that a milliliter is 1,000 compared to the liter. So if I divide 95 by 1,000, we'll have 0.95 liters, and that gets placed down here. Grams over molar mass is our mole. Mole divided by liter is our concentration unit known as molarity. Shall we hit that together and see what we find? I bet it will be 1.3 because our screen says, but let's confirm. 5 divided by 40 is 0.125, divided by 0.095, and I get 1.3157, so rounding to 2 sig figs, 1.3 big M molar units. Molarity, the other one was asked as mass percentage. Remember, this definition is the mass of the solute, which was 5 grams, over just the mass of the water, and that's 95 milliliters. But remember, the density of water was 1. So even though it gave us milliliters, I understand that's the same as saying 95 grams of water. So even though this is 95 mils, that's equivalent to saying grams. So we had 5 grams of the NaOH over that 95 grams of the water. On the bottom here, we'll just simply show that in addition to the 95 grams of water, there was 5 grams of the solute, giving me a total mass of 100 grams of solution. And that's where you find 5%. Thinking just part over whole, so 2 parts over the whole here. What is the molarity of glucose in a solution containing 126 milligrams of glucose per 100 mils of solution? This is a model problem from your text. Let's take a peek at it. I want big M, molarity. Molarity is defined as moles of solute per liter of solution. Moles itself is grams over molar mass. And we'll just keep that ratio all over the liter. We weighed out 126 milligrams, and I know that it has to be a gram to fit into my mole calculation. The prefix milli represents 1,000 grams. It's going to be quite a small number, but I have to just slide that decimal 3 places over. So 126 divided by that 1,000 is 0.126 grams. See what we've done here? We've converted our milligram to a gram by sliding the decimal 3 spots. That's not a decimal, by the way, although it looks like a random dot. What we're trying to do is erase that 1 gram over 1,000 milligrams is that ratio there. And now that we have the grams, we'll also need to do a little work with the molar mass to be able to pull out moles. We have to sum 6 carbons, 12 hydrogens, and 6 oxygens. And I can do that while the wheel is spinning here. Carbon has a molar mass of 12, and there's 6 of them. So 12 times 6. 12 times 6 plus, we have the mass of 12 hydrogens, so I'll add 12, plus the mass of 6 oxygens, which we can see to be 6 times 16. So I'm getting 180 as that molar mass there. See what I've done as I was waiting for that wheel. Carbon, there's 6 of them, and carbon weighs 12. Hydrogen, there's 12 of them, and hydrogen weighs 1. And oxygen, who has a weight of 16, but there's 6 of them, I just summed all that up and got 180 as my molar mass. Let's keep going. 0.126 grams of solute over the molar mass of 180 is mole. this is 100 milliliters, so 100 mils has to be converted to a liter. And again, the milli, just as in the milligram, we know a milliliter is 1,000. So 100 mils is 0.1 liter. I take my 0.126, I'll divide by the 180 molar mass, and I'll divide by 0.1, the volume in a liter, and my calculator says 0.007 molar. Big M is our unit, molar. Their answer is 0.00699. That's what this value is, 0.00699. My calculator rounded for me. Same number in my opinion. We have a 4.49 gram sample of a laboratory solution that contains 1.85 grams of acid. What is the percentage? So I have 1.85 grams of the acid. Now you notice how I'm using that as my solute because it's what I have the least of over the sample entire weight, which is 4.49. And we want that as a percentage, so we'll multiply it by 100. So we have 1.85 grams of solute divided by 4.49 grams of the whole sample expressed as a percent. If you're like me, my answer is about 41.2%. How are you doing there? We have a 3.3 grams of solute and 13.1 gram of just the solvent. What is the mass percent of the solute in the solution? This is like an earlier example where we consider the grams of the solute over the entire solution, which contains both components. The solution has two components. It has the 3.3 grams of solute plus the 13.1 grams of solvent. The sum here is the mass of the whole solution. Solute plus solvent, and again they want it as a percent. So our 3.3 divided by the sum of 3.3 and 13.1 expressed as a percent. If you're hitting with me, I hope. Does your calculator say 20.12%? And we continue. Calculate the molarity of the following solutions. Well, the molarity we know to be defined as moles of solute per liter of solution. What's nice here, they're giving me the moles as 0.35, and it's directly giving me the volume in a liter, so this is a pretty straightforward calculation. 0.35 divided by 1.5, and we have a 0.23 repeating molar solution. Here we have to do a little bit more work, don't we? 20.1 grams of magnesium sulfide. So here we know that moles per liter, but mole is defined as grams over molar mass. So we have a little mole map work to do before we can divide by the volume. The grams was 20.1. And we need this molar mass. Let's see, magnesium, find it on your periodic table, second column down, couple, so 24.3. And sulfur, look to the right, see its value is 32. So 0.36, we'll say the molar mass is 56.3 grams for magnesium sulfide. And it was nice because we just had one of each of those atoms. So the sum of 1 mg added to the sum there of sulfur. And how about 759 milliliters? We're learning that we just simply slide, don't we? 759 liters with the point value here, 0.759. So we'll try that out. We have 20.1 divided by 56.3 divided by 0.759. I have 0.47 molar. Hear how I'm saying that? Big M, 0.47 molar units. Doing great job. Again, calculating the molarity. This is a straightforward calculation, moles per liter. Here we have a little more work to do where we have to turn grams into moles and then divide by 0.847. I'll let you try these two on your own. Same example exactly as the previous slide. First one, of course, 0.55 divided by 0.205. I didn't say that right. 0.55 moles of solute divided by 2.05 liters. Pretty straightforward, moles per liter. Here you have to do a little mole map work. You have 14.7 grams of salt. You have to divide that by the molar mass of NaCl and then place that over the liters of solution. So here you have to add an Na and a Cl, which we did just a minute ago. Grams over molar mass per liter is your big M calculation. So you have lots of practice there in terms of concentration units, both in our lecture and in your sapling, and I'll let you look at those. The section 5.6, a closer look at solutes, we're going to tackle this with a series of videos that you'll see. Section 5.6, a closer look at electrolytes, and then also when we get to the nomenclature, I'm just kind of previewing here, there's a series of lessons that are different clicks, and you'll see them coming down the slide a little bit further on your Blackboard page, but I'm going to take you through a very detailed lesson of what it means to be an electrolyte, strong and weak, and there's even a little animation video I want you to watch on ions and aqueous solutions. I want you to also take a look at ions being formed, atoms to ions, and this is going to be called the ionic nomenclature series. So after this particular lesson is complete, your job is to tackle its Tyler DeWitt in ionic nomenclature, and then also the electrolytes, which is my voice. When you're completed with those, come back to the Blackboard lessons in this series.